Oh, no worries. Well, the reason I wanted to go through that math and physics with you is I thought it was something digestible and a quick presentation that is directly relevant to one of the other projects I was working on while I was a postdoc in the Intelligence and Space Research Division. Here I was looking at fast neutron imaging, and this is something that's directly parallel to the medical X-ray imaging that you would, go to the dentist and get your teeth X-rayed, or if you broke a bone. But we're doing it with a different interrogating particles. Instead of X-rays, we're using fast neutrons. And I mentioned this before, but different materials have different cross-sectional properties. And remember that cross-section is kind of a measure of how likely a particle is to interact with a material in that volume. And these properties change as a function of the particle type. Are these neutrons? Are they X-rays? Are they higher energy gamma rays? And they also change as a function of particle energy. So on the right, there's this plot here where I've got 3 different colored lines, and I should have labeled these better for this audience, but DT, these are 14 MeV neutrons, and then the dark blue line is looking at 1 MeV gamma rays, and then the light blue line is looking at 3 MeV gamma rays, so different energies and different particles. And on the x-axis, we're looking at Z, the Z of the material that we would be looking at. So 1 would be hydrogen. The 3 dots all the way on the right that you can see, that's isotopes of uranium and plutonium. And then the cross-section is on the y-axis. So you can see that there's a very different cross-section profile depending on what material you're looking at, that's the x-axis, and then what particle you're using to interrogate that material, that's the colors of the line. And basically what this project was doing was exploiting these differences in cross-section to interpret radiographs that were taken with neutrons. So on the bottom here, this is an example radiograph that I took with a system that we built at LANL, looking at, well, what they call this is a step wedge. So this is a copper piece that has increasing thickness. And then we call that a spatial target, trying to see how good a resolution is with this imaging system. So we did a lot of detector characterization, measurements of objects that we cared about, and the skills and knowledge that I had to use for this project, something completely new to me was imaging theory and how to quantify how good your image quality is. That was a really interesting thing to work on. And it turns out we're really benefiting from a lot of advancements that have happened in medical physics because there's a lot of money to drive advancements there. So I got to learn a little bit about medical physics and medical imaging there. Image processing, that's also something I hadn't done before. And really interesting about this project for me was the concept for this project was a proposal that I had written for a funding agency that got funded, as did a follow-on project. So getting experience writing proposals and engaging with sponsors was really beneficial for me kind of early on in my career. And it was a really neat application too, so I like that. All right, the last project I'll talk to you about just a little bit, it's called the Diorama Project. This is one that I worked on while I was a staff scientist in the Intelligence and Space Research Division. So I'm not sure how familiar folks are with the Limited Nuclear Test Ban Treaty, but it was signed in 1963. So here's a photo of JFK signing that in the upper right-hand corner. And the language of this treaty prohibits nuclear weapons tests underwater, in the atmosphere, or in outer space. Well, great, we've got this treaty, but how do we know if other countries are breaking the terms of this treaty? Well, we've got this program called Space Nuclear Detonation Detection, or SNDD. And fun fact, every GPS satellite that has launched from the US has radiation detectors for treaty monitoring and verification. So we have the ability from space to determine if countries are adhering to the Limited Nuclear Test Ban Treaty. So I think that's pretty cool. And there's a lot of work that was done, or that is still done in the group that I was in ISR, developing these radiation detectors. So we have neutron, prompt gamma ray, delayed gamma ray detectors on a certain set of satellites. And then we have X-ray detectors, optical detectors, EMP detectors on another set of satellites. And there's a lot of work that goes into coming up with the concept for an instrument, testing it, getting it integrated into an instrument, then getting it integrated into the satellite, and then making sure everything is working once it's up on orbit. These things have a pretty long lifetime. So it's a very detailed and involved program. But one of the more interesting projects I worked on in this arena was Diorama, which stands for the Distributed Infrastructure Offering Real-Time Access for Modeling and Analysis, a kind of a forced acronym here. But what this project was, it was a physics-based simulation of the performance of our space nuclear detonation detection constellation as a whole. And I say it's physics-based because we were developing models that would do things like propagate how X-rays and neutrons would travel through the atmosphere to get to a satellite. We were doing things that were propagating what does the EMP signal look like, and is that going to get disturbed as we try to send signals back down to Earth? So there was a lot of physics going on here, not just straight up coding. And this tool allowed us to do really important things like evaluate the system performance against new and emerging threats. You know, if country Y has come up with new weapon X, how well would our full system perform against that type of threat? And up in the upper right corner, this is just an example figure of, you know, if something were detonated in one of those cells, the probability that we would detect it is indicated by color. And this is just something that's completely made up just to show you. We're looking at what we call global coverage. So that's saying, you know, can we see things no matter where folks are doing illicit testing? That's just an example. But other cool things we were able to do was evaluate system performance as a function of time and as a function of new launches. And sometimes we're finding, you know, launches get slipped back. How does that affect our performance? We were able to simulate expected radiation environments that are seen by the space-based instruments, which is really helpful for those folks who are designing the next generation of instruments. And then ultimately, we were providing recommendations to the Air Force, who owns this mission. So I thought this was a really neat project to get involved in because it involved many different types of radiation. It involved me learning a little bit about the physics of what does it look like when a nuclear explosion happens. And it gave me a completely different set of skills I didn't have before. I was a pretty poor programmer in undergrad. I wish I had paid more attention into the analytical physics class that we had. But hopefully I redeemed myself in this project. I was learning C++. Version control is something that I will never go back and not use version control. I found it really helpful. Doing radiation transport modeling, that's a big kind of constant throughout my career so far, but also documentation and communication. This is probably the biggest project I've worked on to date, and being able to write down what I've done, what questions I have in a way that is available not only for posterity, but available for my colleagues and coworkers to comment on, provide peer review on. It's an absolute essential.
Amanda?
Yeah.
So what exactly is version control?
Version control is a way to manage pieces of code when multiple people are working on. Well, it doesn't have to be multiple people, but it's really helpful when multiple people are working on it. And I don't know if anybody's ever had this issue where, say, you're writing a PowerPoint presentation and then you save it, and then you save the next version as underscore version 1, and then you save the version after that as underscore version 3, but you forget which one you're working on and it causes confusion. Version control is a way to be very clear about what exactly you changed, when you changed it, who changed it, and how that affected the quality of the overall code. So I think it's a best practice for coding that I was not aware of and had no reason to be aware of until I was on this project.
Thanks.
Yeah. Okay, let's see. How are we on time? Okay. I thought, unless there's any questions on like the science or physics of what I showed, I can jump into the kind of some lessons learned I collected here.
Yep. And we can always double back. People have lots
Excellent.
of questions at the end. Yep.
Okay, great. So one of the things I kind of wanted to harp on is participate in as many opportunities as possible. I mean, you just heard about some research opportunities, potentially in astrophysics right in your own backyard. That sounds awesome. I was also really lucky. I got to participate in a research experience for undergrads while I was at Oneonta. And even though I'm not doing anything related to the research I did during that summer, it really helped to build my professional network, and it exposed me to new areas of physics I would not have known about otherwise. So I'm really thankful for that opportunity that I had. I would also highly suggest to go to as many seminars as you can wherever you are. There was always something to learn. I've gone to, chemistry talks where I've learned about best ways to represent some of the data analysis I was doing, or material science talks where they've discussed in detail about how radiation interacts with matter in a way that I never got before. There's always something to learn. And especially during COVID time, I think a lot of things are happening online and it makes it easier for us to participate. So I'd strongly encourage that. Another thing is reading journal articles, and this is twofold. The more you read journal articles, the easier it is to actually write them when it comes time to do that. But it also exposes you to new topics that you might not know you're interested in ahead of time. I found that to be one of the more difficult things in choosing a graduate school, because I thought really strongly that I wanted to go into theory like the work I had done with Dr. Fox, but I wasn't 100% sure. So I chose a university that had a lot of different things going on, like at UNH. Maybe if I had started reading journal articles earlier, I would have found my field earlier, but I wouldn't go over and change anything about the path I took. I'm just saying it's an opportunity to learn more earlier on and start to cultivate your own priorities. I'm not so sure how much I heard this when I was in grad school, but don't forget to develop your soft skills. I found that a lot of the reason I've been successful is, partly because of the education and preparation I've had in a technical way, but also because I've spent time developing my soft skills along the way. The ability to communicate with your peers, your mentors, your managers, and sponsors, people that are giving you money to do work, it's absolutely critical for success. So while you're an undergrad, take your reports and your presentations really seriously. This is practice for a very real skill. This is not just an exercise to keep your time occupied. The other thing I might suggest is, while I was at Oneonta, I took a public speaking class, and it was a general gen ed requirement, but I really, really hated public speaking, and I still don't really like it, but it helped me to develop a lot of skills and ways to prepare myself that I still use today. So if that's an opportunity for you, I would highly encourage you take a public speaking class. Learn to take constructive criticism with grace. I would say 99.9% of the people I've interacted with in my career have wanted the best for me and for my work. They are not pointing things out because they think I'm stupid. They're pointing things out because they want my work to be better. And I think I've seen a lot of folks, especially new folks, come to the lab who get very, very defensive when somebody tries to comment on their work. And I think I'm really proud that I have the ability to take constructive criticism and apply it so that my work can be better overall. So something to think about early. The other thing is, I mentioned this earlier, learning to persevere, really making sure that you're putting in the time, you're putting in the effort, you're working really hard to deserve the accomplishments that are to come. But on the flip side, know when to ask for help. There's a point when it's just silly if you're banging your head against a wall. And you know that there's somebody who would be able to answer this question in 30 seconds down the hall. So it's kind of a difficult line to cross. And I think undergrad is a great time to kind of learn where that line is between figuring things out on your own and learning when to ask for help. But to go back to my earlier point, there's never been anybody in my career that I've asked for help that said no. So take that. Hopefully you guys find the same thing here. This is a big one for me. Cultivate your organizational skills now. Being able to go back and find my notes from 2 years ago, or even my undergraduate notes, and being able to actually get something out of them, that's really helpful for me. I benefit for it because I have the absolute worst memory of all time, and I can't remember what I did a week ago, let alone a year ago. But it also helps my peers because I'll take really good meeting notes or write reports before I forget to do things. I think organizational skills are an easy, low-hanging fruit skill to develop, but it's not one size fit all. So figure out what works best for you and tweak it as you go through your career. Another main point I really want to bring up is become a team player. Know that you are part of something bigger than you. This kind of goes to taking constructive criticism, doing things that will help out your career, will also help out your neighbor. will help out your mentor, help out the project that you're working on. But the flip side of that is don't let others take advantage of you. I'm very lucky I haven't had this experience, but I've seen it from other colleagues when I was in grad school. You are not cheap labor. That is not the point of being a grad student. The point of being a grad student is to become the next generation of subject matter expertise. So, pay your dues, put in the legwork, put in the hard work of learning things from scratch, but understand that there is a point that it's not fair that others might be taking advantage of you, and be on the lookout for that. That's not okay, especially with people being so aware as they are in 2021. Just something to keep in the back of your mind. I'm fairly certain you're not going to encounter it in Oneonta, but for grad school, be a team player, but don't let others take advantage of you. This is another one I wanted to kind of harp on. Take care of yourself. A career in science is a marathon. It is not a sprint. Part of that is treating your body right. Your body takes care of your brain. I mean, there have also been pretty big ideas that have come to me while I was on a run, just getting away from the computer for a little bit and letting my brain have time to relax. Really, please, everyone, take your mental health seriously. Get help when you need it. This can be a very stressful field. Graduate school can be very difficult. Doing a postdoc is also hard. There are opportunities and resources all along the way to get help. Please look inward and recognize when things come to a point that you need to get help yourself. And look for that in your colleagues too, and care for them and look out for them too. I had somebody that I actually dated in grad school took his own life in the last year. And it was a really sad state of affairs. And it just kind of told us all that we need to pay more attention to this within ourselves and with others. So please take it seriously. Along that vein, continue to adapt and learn ways to handle stress, whether that's taking some time away from the computer, getting some time with your furry friends, getting time with regular friends, and finding other outlets or activities to pursue. I think that's also really important to keep yourselves well-rounded so that you can have a more full career in science. And then I just wanted to really briefly tell you guys about some neat opportunities that exist at Los Alamos National Labs. This is a slide I put together when I was talking about DOE laboratories in general. So the Department of Energy has many different laboratories. Here's a map down in the lower left. Of these laboratories, there are 3 that are weapons laboratories. So that's us, Los Alamos in New Mexico, Sandia in New Mexico, and Lawrence Livermore in California. So we kind of have a different set of really neat resources on our own. But the DOE complex, like we call it, gives you so many wonderful scientific opportunities. You get mentorship from top scientists in their field, collaboration with world-class scientists, access to world-class resources and facilities. So here on the right, I'm showing the 2 versions ago, our supercomputer, them assembling that. And then we've got the Los Alamos portable pulsar. That's the kind of satellite dish looking thing in the bottom of the L, in the corner of the L. That picture that kind of looks like the mountains, that is in Los Alamos. That is the Los Alamos Neutron Science Center. So that is a proton accelerator facility that they use to create spallation neutrons to do a lot of really cool imaging and nuclear interrogation type work. And then other world-class resources, we have our high-performance computing, and then all the way on the very right, we have state-of-the-art ways to display the simulations that we perform for others to see. That's a room that is completely covered, 360 degrees. You can get inside your simulations, actually. Other cool things that I've seen at Lanolin, I've been participating in interdisciplinary projects. I myself have worked with people that are more basic physics, that are material science, that are space science, that are plasma physicists, astrophysicists. I mean, you name it. We have so many different kinds of scientists and so many different kinds of interdisciplinary projects. Another neat thing is there's collaboration within the DOE network. So I've collaborated with folks at Sandia, Livermore, Jefferson Lab, Brookhaven. I think that's it. But PINA now, Pacific Northwest National Lab. you're effectively multiplying your network by a factor of 12 just by coming into this DOE fold, which helps you to build a professional network. And another thing is there's a lot of internal as well as external funding opportunities. So the ability to write your own proposals for work that you think is important exists, but you can also work on existing projects and programs that have been around since the 60s. Future prospects for folks who are in undergrad or in grad school, lots of professional development opportunities. So many seminars are going on. I probably get 12 emails a week just on neat seminars that are happening. Lots of workshops that go on. So you get lots of subject matter experts in the same room in order to really drive progress in an area. General skill development. I think what I meant there was kind of the soft skills. So the opportunity to present your work, to write down your work in internal papers, things like that. And coming here as a student or as a grad student or as a postdoc is an excellent step towards becoming a staff member, which I cannot say enough great things about. The other nice thing about Lanel and the DOE complex in general is the quality of life here is really, really high. There's a very competitive compensation program. There's excellent benefits. The work that we do is I find it very meaningful and very important. And there's a lot of very diverse communities that are going all over this DOE complex. And depending on what type of lifestyle you see yourself leading in the future, there's a lab there to meet that. So I'm not really a huge social butterfly. I really like being in the outdoors. Los Alamos, New Mexico is a great place for that. If you're a little bit more wanting to go out to restaurants and go out for drinks at night, Lawrence Livermore near, is it near Berkeley? I can't remember. I can't remember what the big city is there, but they're much closer to folks who are that have bigger city life. Brookhaven's close to New York City. That's on Long Island, things like that. So there is a DOE lab to fit your needs. And then specifically at Lanel, there are several undergraduate research opportunities. Generally, these happen year-round. It's not just the summer. There are GPA requirements which change depending on which opportunity you're looking at, and it does require that you pass a drug test before they'll extend you an offer. But there are things, and I've got links here I can send to Dr. Gallagher to share with you guys if you're interested. There are both general job ads and also specific job ads to work on specific projects. And those are available to look at all year round. There are also a few specific summer school opportunities for undergraduates and graduates. Things in summer schools in data science, dynamics, that's supposed to say, nuclear forensics, space weather, computational physics. These are like 6 to 12 week programs where you come out and you get paid to do research and work with some of the foremost experts in these fields. Another thing that I thought might be of interest to this community is the Post-Bac Opportunities. And I just copied this text right from the webpage. These opportunities exist for those who have been awarded a bachelor's degree within the past 3 years, but they have not yet been accepted and enrolled in a graduate program. And the benefit of this is it gives you some time to get some real world experience while you're doing things like studying for your GREs and taking your GREs and preparing your materials to apply to grad school. So that's a really interesting program that I hadn't heard about before I went to Lanel. If that's something that you're interested in, as with any of these opportunities, please feel free to reach out to me. I'd love to talk more about them. There's also, beyond post-bac opportunities, you can come here as a graduate student. There are certain universities that work very closely with Lanel, or you could do like I did, come here for a postdoctoral appointment. And that's basically an opportunity. It's usually 2 years, sometimes it's 3. And I really try to describe it as a trial period, both for you and for the laboratory. You're kind of feeling out, is this the right thing for you? Is this the right place for you to live? And it's kind of that stepping stone from getting your PhD to becoming a staff scientist. So that is all I had prepared. Thank you guys so much for joining me. I really love talking to you, and I love having the opportunity to reflect on how great SUNY Oneonta set me up for success in what I'm doing now. Like I said, if you have any questions at all, please feel free to email me. I would love to talk more.
Thank you very much. That was spectacular. And I have to say before and people get your questions ready. but I was thinking when you were talking about um, the test ban treaty, um, which its existence uh, has supported your work in some ways.
Yes.
And it also was a, uh, my PhD thesis was a direct result of it because in when that was signed, uh, there was a radar that was built at Stanford University to look in the detonation clouds to get electron densities of above ground tests. And when that treaty was signed, that instrument's placement at Stanford became useless. So they packed up this radar and shipped it off to Alaska. And then after 11 years in Alaska, they shipped it to Sandströmfjord, Greenland, which is where I uh, used it. But um, the in Puerto Rico, the radar that was in Puerto Rico, the giant radio telescope, was actually an incoherent scatter radar. And all the incoherent scatter radars around the world are set at around 400 megahertz. The one I used was at 1200 megahertz because it was designed for a different purpose.
I
But
see. And that brings up a really a point I didn't mention earlier is depending on where things are being detonated, that tells you what signatures you might actually see, and that changes what diagnostics you might do. So if things are kind of lower in the atmosphere, you're not going to be seeing a lot of signals from space because there's a lot of atmosphere to go to before those signals get to your satellites. If those detonations are happening underground, we have seismic I want to call them constellations, like suites of detectors that are set up to be able to detect if somebody's setting off things underground. And what you were just talking about, Dr. Gallagher, that sounds like it's more of the close to Earth atmosphere. And
it was ionospheric stuff
ionosphere.
and magnetospheric stuff, which of course is your lab is also famous for, as you described in the space weather areas.
Yeah.
Well, if other people have questions, you can unmute and ask. Dr. Fox is going to get to go first because I know he's got one, so we'll start with that. Or you can type them in the chat and I'll relay them.
No, well, thanks a lot for that. And Amanda, that was fantastic. That was just an amazing talk. Professional. I think it makes us all really proud. I mean, I'm inspired. I wish I was you.
My life is pretty
Yes.
great.
Yeah, no, that's really great. A couple things. First of all, when you showed that picture of JFK signing that treaty, there was about 20 people in that photo, and every single one was a white man wearing a suit, which is kind of interesting. You know?
Yes. I will say
So-
Lanel it's making a lot of strides toward diversity. It has a lot of programs to help increase diversity of all kinds. And I think we're slowly seeing our demographics change.
So let me just quickly ask you a couple quick questions.
Yeah.
What is you said a spallation neutron or a spell?
Oh,
What is that? What is a spallation neutron?
okay. A spallation neutron source. What happens is, so neutrons don't have charge. It's hard to accelerate them in an accelerator like you would something that has charge like a proton. So you'll bring in these protons and you'll accelerate them to 800 MeV. I'm not sure if that means anything to students, but it gets 800 MeV and then it smacks into this tungsten target, and then it releases all of these neutrons out the other end. And that's what's called a spallation neutron source. It's that process that's called spallation. And we would get neutrons, you get really cold neutrons, so less than an EV, but the neutrons I was interested in went from about 1 MeV up to 600 MeV. So really, really fast neutrons. We were calling them ultra fast.
One other question, because I know other people have questions too. The projects that you work on, are they directly related to whatever these SNDD satellites are doing, or is that just something you mentioned? Like,
that's just one of the things that I mentioned. So that Diorama project I mentioned is directly related to space-based nuclear detonation detection. I worked on a few other things in that regime too. But the neutron imaging that I was telling you about, that's actually this is actually something kind of cool. I'll just take a second to talk about it. There are people whose expertise allows them to be responders. If somebody were to find a box on the side of the road, they thought it had some signature that looked really suspicious, they're actually calling people at LANL to say, hey, what is this that we're looking at? Is this something we should be worried about? And the project I was showing you with neutron imaging is another way to try and diagnose, well, what's in that box? Should we be concerned? What actions do we need to take from here? And actually, the reason I've gotten my COVID shot early is because I am in training to be one of those nuclear emergency responders that has 1 hour to show up to our classified area to start getting that information and data and start telling people what the best course of action is. It's pretty cool.
And pretty scary.
But less scary because you know that that
Yeah.
resource exists.
Yeah. Yep. Fair enough.
I could ask a lot of questions, but I think I'll let somebody else go.
Okay.
Daniel, I thought I saw you typing. Do you have a question?
I can look at the screen.
Okay, yes. What are nuclear forensics and their application?
That is a great question. So a lot of the work that I'm doing, we call it pre-boom. So it's trying to deter other countries from setting something off in the first place. And the fact that we have satellites up that can constantly monitor the globe is a form of deterrence that means hopefully people will never do any testing above ground. If something were to happen though, there are people, and most often they're radiochemists, sometimes they're physicists, who would be able to go and collect soil samples and be able to determine what was it that actually happened, what type of device do we think this was, who do we think might have done this. So that's what nuclear forensics is.
It related to that, the last above ground test, I want to say that was the French circa 2000.
I don't know that for sure.
But so
2000
or the French, oh no, it was below ground. Well,
so that's where things get really tricky. So we still do nuclear tests, but they do not produce nuclear yield. That's where things get, so for example, we'll do things like replace all of the plutonium with something inert, and you can test the explosives and you can test other things, and it's related to nuclear, but you're not actually producing nuclear yield. And I believe the 80s is when comprehensive test ban treaty was signed but not ratified. So we have not been doing things for quite a while.
Okay, I remember it might be 1996.
Oh,
Yeah, I think
that might be it.
I think that you're right, because I think that there was a late French test that was largely in violation of the treaty.
Yeah, no, I think that's true. And
I believe you. I'm just not familiar.
I don't remember the exact date. I do remember in the 1980s at one point I was driving through New Mexico. We were going past Los Alamos, and we were actually stopped behind the mountain, and then we heard a big loud rumbling sound. It would have been 1987 or 1986.
I
So
still
it
hear
might have
them
been
from
actually
my
a
house.
nuclear test.
Well, I don't hear the nuclear test from my house. I hear the explosives test from my house.
It could have been that too. We were just told to stop on the other side of the mountain from whatever was going on the other side.
Oh, funny.
yeah, but I was thinking that a test like that would be a tremendous opportunity. While in violation and bad, it would be a tremendous opportunity to.
So here's the thing. We have done more nuclear tests than any other country. And while these test ban treaties are in effect, we have all the cards. We have the most information, the most data. As soon as we allow other countries to test, if we were to say, hey, we're going to back out of this, that would allow other countries to catch up. So that's another reason why the US is okay with this moratorium on testing. So I'll speak really briefly about my new job. There are these really complex multi-physics codes that go on. And one of the things that we do is we simulate things and compare the results to prior tests and see how well they match. And we use that as an opportunity to develop code and better understand physics.
You mean historic tests?
Yes, historic tests.
Yeah. Oh, cool.
Mhm.
That's interesting.
And it's very theory-based, Mike.
Do any of the other students have a question? Nick, Shabam, Hadley, Mitchell? Yeah, they're quiet.
Can we ask a question?
Yeah, of
Of
course.
All right, cool. Well, I'll let
But
Melissa ask.
it'll be
She's not-
$1.
Okay, I'll let you go.
Okay, I guess I was just wondering if your work had any applications with nuclear power plants, like if your detection method could be used in detecting leaks or things like that, if people were going to use nuclear power as a viable, more
Yes.
green energy resource.
So in the Department of Energy complex, there are more, other sites are more into active research in nuclear power. We have some things that we're working on. Actually, we built the reactor that went on to Curiosity, which is cool. So we build reactors for special things like that. One thing that you can do, so I've spoken a lot about kind of this global security thing, and a lot of the work that I'm doing is preventing proliferation, making sure people aren't doing things they're not supposed to do. One of those things is making sure countries that do have nuclear power plants, are they diverting material to do something bad with it? And there are lots of signatures that you can look for when you're looking at a nuclear power plant. The IAEA, the International Atomic Energy Agency, goes and inspects these facilities. And you're only allowed a certain amount of access to their materials and things like that, but there's an active area of R&D at LANL is determining what signatures can we look at from this power plant if we're viewing it from afar to see if folks are doing things they shouldn't be doing with that material.
Okay.
Does that
Thank
answer
you.
your question?
Yeah, that answered it. Thank you. I was just curious.
Let's see, we might. Okay, so this is from the chemist I want to recruit. Are there any special chemical signatures that you look for when looking for nuclear explosions, like when you take soil samples?
Yes. So it's not so much chemical signatures as it is radioactive signatures. We are looking at what isotopes what isotopes were created in the explosion, and then how fast are they decaying. So I guess you could call that chemistry, not just we call it radiochemistry because it's kind of a little bit of both. So you have things that decay really fast. You have things that take a longer time to decay that are easier to measure. What ratio are those radioisotopes in? And then the really difficult part is, one radioisotope will decay into another radioisotope, into another. So it makes like this chain, but then you have multiple sources of where these different daughters and mothers of radioisotopes are coming from. So it's a really, really complicated process. And we definitely have a lot of chemists at the lab who are involved in either active research and development in this area or keeping that capability ready to go if it were necessary.
And I imagine that type of process that you're talking about would have amazing modeling efforts because it essentially giant chemistry models, almost like atmospheric chemistry models.
Yes, and we are a big driver because we're a big consumer of nuclear data. So when you hear about people doing basic physics research, they're slamming protons into random isotopes of helium or aluminum or whatever, and they're coming up with what the cross sections are, what the decay rates are. We are a major consumer of that information because the fewer uncertainties we have and what the decay chains are, the better we can pin down what actually happened.
Anybody else? I have lots. I'm like Mike. I can
stay around for a while. I love talking about this stuff.
So I was wondering, totally separately, you grew up in upstate New York. You went to school in upstate New York. You made the huge, enormous jump to New Hampshire. When you got the offer for the position, at Los Alamos, were you nervous? Was leaving the region a hard decision?
To be honest, I probably spent the first 2 years being really homesick and trying to come back home. Um, it was very new. It was very new to me, and it took me a little bit to settle in to my postdoc. That was definitely part of it. Partly, I was missing fall in New England. I missed water. But we're not the desert. We do have 4 seasons here. I think some of that was just the normal. I moved to a new place. I didn't have friends yet. I didn't really feel rooted, like I belonged there. And I didn't really, well, I didn't have a clearance, so I didn't really understand a lot of the motivation of the stuff I was doing. And I didn't feel like it was as important as I do now. So yeah, it was a hard transition for me, but I look forward to going and seeing my parents. They still live in Saratoga. I see them, well, if it wasn't COVID, I'd see them at least once a year. Turns out there is some water around here. There's Blue Hole, which is, as it's named, a great blue hole, where I learned how to go scuba diving. So I think you kind of learn to make the best of wherever you go. But for me, and hopefully this can be a lesson learned too, I didn't write down, give things a little bit of time before you give up on them.
Amanda, you said that your group or your lab, they built the reactor for Curiosity. You mean the Mars rover?
Yeah. Wait, was Curiosity, what was the most recent one? Was it Curiosity?
Curiosity and Perseverance.
Perseverance. So they might have done Curiosity too, but they definitely did Perseverance.
Okay, I didn't know those things had like nuclear reactors on them.
Mm-hmm. So the problem is you can't put solar panels on stuff when there's particulates in the sky preventing you from getting a lot of sunlight. So there is a whole group out here that does nuclear reactors for space assets.
Dr. Fox needs to read The Martian.
That was a good book.
The movie is good too.
The Martian, like from the movie with who was it? Matt Damon, that movie?
Yeah.
Yeah, I saw the movie.
But well, the movie's enough to tell you, but the book is really the book is like a general education course.
And quick plug, one of the instruments that was on Curiosity and on Perseverance, there's two kind of generations of it, is called SuperCam and ChemCam. That's a Lanel lead instrument that's on the Mars rover, which it uses. It basically uses a laser. It makes a little plasma at the rocks, and it does spectral analysis of the Martian rock composition. It's cool. That's my group. So if that's something that interests you, we do cool basic science stuff at Lanel too.
From Daniel DeJesus Minierte, again, he's a big question asker. And
Good.
Yep. Could you explain the process of technology demonstrations for space-based X-ray detectors again?
Ooh, I'm not
I guess the technology, could you explain the technology, let's say, for space-based X-ray detectors?
Sure. Somewhat. So we have several different X-ray detectors that are on our GPS and other satellites, and they are what we call flash X-ray detectors. So what they're looking for is a big flash of X-rays that happen out of nowhere. And that's indicative that there was a nuclear weapon explosion. It's also indicative of gamma ray bursts, which are a source of background for these types of instruments. So that's I want to say a galactic phenomenon, but that might not be the right term.
Extragalactic.
Extragalactic. Thank you. So what these detectors are looking for is basically there are solid state detectors. They're made of silicon. There's displacement in the silicon lattice when you get X-rays interacting in the lattice, and you can detect that displacement when they try to recombine together. And that signal that you look at as a function of time, so you start getting a lot of X-rays, and then you get even more X-rays, and then your signal kind of dies down. They can look at that signal and say, well, is that characteristic of a nuclear explosion? And hopefully what they can do is say, you know, we're seeing a signal, but that might be a galactic cosmic ray. And the nice thing is we have other instruments that we can kind of do truth testing against to say, oh, our X-ray saw it, but our optical didn't, or vice versa. So we have some truth testing on board, but the instruments themselves are solid state, silicon and other materials, flash X-ray detectors. Does
And
that answer?
yeah, he's typing, but I think that was great. And that would also explain why he says, "I understand!" Exclamation point. That would also
Oh, good.
explain why your lab has a great deal of interest in actually monitoring solar activity, so that you can discriminate between nuclear sources and non-nuclear sources,
Yes,
which is
there's
what you said with the extragalactic.
Yeah, and there's a lot of work that's done they don't like being called space weather, but it's determining kind of what are the solar characteristics that are maybe causing, what do we want to call it, decharging of your spacecraft. Like your spacecraft can charge up and then de-excite, and that causes a background too. So we've got folks that are looking into what are the surrounding environments and could that be a cause? Another really cool area of research, space weather.
Yeah. The spacecraft charging is
It's a big problem.
big and not well understood.
No.
From Nathan, Melissa and I have to go as we have the never-ending but fun grad to do. It was great seeing everyone. Definitely made our week for sure. P.S. Mike, I look forward to the email, and we can always chat on Zoom as well. But I think he just wants you to know you owe him an email. And I sent him it, so I win. Any other questions? Well, I would like to, Shivam, do you want to chime in? You can turn on your mic. None for me. Okay, it looked like one. Well, I want to, what's that?
Hugh, it's Charlie. I have a quick one for
Okay.
Amanda. It's not a physics-based question so much as how you doing. As how badly was the lab impacted once the pandemic really set in? Were you guys literally shut down, or how did that work in sort of the real world?
Yeah, so we it kind of trickled in, and then we were told to all work from home. And depending on where you were working, that was okay. You know, there's pros and cons to wherever you work. I think industry is much more on top of state-of-the-art tech, and we're a little bit behind. So getting access to all of our networks and our HPC resources from home was really difficult because we've never had to do that before.
Right.
I wasn't hit so bad, but there were a lot of people who all of a sudden had no work that they could do because all their work was classified. So I think we're starting to get back. I think we're at the 50% level, back occupying buildings. It was rough for a really long time. We had a charge code that people could use if they only had classified work to do and they couldn't do anything from home, so that they could still get paid. There was a charge code people could use if they had small kids and they needed to take care of their kiddos and they couldn't be as productive as they normally would because childcare is closed. We had charge codes if you actually came down with COVID, or if you had to isolate because you were in contact with somebody who had COVID. So I think I really am, everyone will find a reason to complain about something, but I think Lanel did an awesome job navigating these uncharted territories, getting us a lot of work that we could do, a lot of professional development opportunities that you could do unclassified if you had nothing else to do, and then really safely transitioning us back to work. I've been really impressed, honestly.
I could imagine the classified issue would be a big one, but also just, I mean, the kind of research that needs attention, right? There's things that people are building or materials that have to be, I would assume, looked in on, right, from time to time, and not just left their own devices. That people might have lost, valuable work they were doing. That's what I was wondering if you heard of
I didn't
like
even
that.
think to mention the experimental side of it. I think that there were some exceptions they were making for certain things like, gosh, we just talked about Curiosity, the other rover.
Perseverance.
Perseverance, thank you. They're trying to get that delivered so that they can launch that. So I think they were making certain exceptions for that. I think they made small exceptions for experiments and equipment that needed to be maintained. But these were like one-off, one person in a room by themselves. They were trying to be as good as they could do. A lot of it was a limitation from the state and the governor's guidance more than the lab, but that's a really good point. That's been another really hard thing to deal with.
Yeah.
Thank you for the answer.
Yeah, nice to see you.
You too.
If you had emphasized perseverance in your talk, then maybe you could remember the name of that spacecraft.
I know, what the heck?
So I want to thank you again for coming here.
My pleasure.
And being a frontier leader for Nathan and Melissa, who are having a great experience, and for sharing your experience with all our students, who I also want to thank for being here. And
Yes,
I gotta echo Mike. I feel very proud. Yeah.
Yeah, we do.
Yeah, it's cool to have you here. And thank you for doing it. I know it's a lot of time, but
absolutely, my pleasure.
Like you said, COVID is taking some things away, but it's given some. We'd be waiting for you to visit mom and dad and then begging you to come down.
Oh, I would absolutely love to. That would be wonderful. And I'll send you a few links too, in case there are students who would be interested in looking at some of the opportunities at Lanel.
That would be great. I've been hoping to revamp our webpage, and I want to. Yeah, don't. But I'd like to put links up to some of these. We had Luke in the fall. We've had we've had about I know he's right down the road, but we've had about 8 people who've come back to give just spectacular talks, and they've been an inspiration. So I'd like us to showcase that a little bit. But if I use any of, if I'm going to post a video, I'll make sure I'll let you know first.
Okay. Hey, let me know if you ask Joe Belarge if he hasn't already done one. I'd love to see his talk.
I thought about that because I'm going to share something with you that we did. I'm going to see if I can share it. Let me see. It's recruiting is different, and admissions things are different. So one thing we spent some time putting together, and I only like this because it looks cool, but it also says a lot of things to be proud of. So
oh, cool.
And so this is where alumni are. There you are.
Oh, how
if I should be using
who's at
something
Sandia?
different. But let's see. Sandia's on here somewhere. There's
Yeah, I
Sandia.
see that. Who's that?
Luke the Imperial.
Stop. Sandia, California, or Sandia, New Mexico?
New Mexico.
No kidding. I had
Okay,
no idea.
I will.
Sorry, that was really loud.
I will tell him to contact you. I just assumed
Please.
you knew.
No.
And I think Joe's at MIT Lincoln Lab.
I think I knew that too. I did delete all of my social media after getting my job here, so that could partly be my fault.
Well,
Oh, that's great.
I will. With your permission, I'll give him your email.
Please do.
Okay, yeah, because he's just right down the road.
Oh, neat.
Well, I guess it's 2 hours, right?
Yes.
Yep. Which in New Mexico is right down the road.
It's much easier driving than driving in New York.
Well, you haven't driven in New York in COVID. It's not so bad.
True.
I
I did see there was a question about bears. There's so much wildlife here. I get deer in my backyard. I see elk all the time. Bears. There was one that came within 20 feet of my camper. Thank goodness my dog was inside. Really just the neatest animals life. It's like what you would think of as Denver-y. It's high mountain desert.
Yeah, yeah, yep. Oh, it's so great seeing you, Amanda.
Oh, thank you for the opportunity to share how awesome Oneonta has made my life.
This is it's great fun, and we'll have you back again soon.
Sounds great. Good luck, everyone.
Thanks, Amanda.
Take care.
Thanks, Amanda. It was just great to see you.
Good
Bye.
to see you
Thank you,
guys.
Charlie.
Yeah. Bye-bye. You got something?
No, I said thank you for joining us.
No, thank you. I was so glad to take part.
All right, I got to sign off, but it was super to see you, Amanda. And
Good to see you too.
all right, so I'll talk to you on email or something. So
Absolutely.
all right,
Sounds
so
good.
see you.
Bye. Thanks.